So, dear colleagues, it's time to start, and today we have a speaker, Mihai Dima, who is okay. So, and the report will be Flash-algorithm in particle physics. It's about track recognition in SPD, simulation, some simulation, I guess. Okay, please start.
I will show you flash algorithms. This means not flash memory, it means fast speed. Where are these algorithms used in particle physics? What's the motivation? Plan for SPD and our straw problem, and why is XYZ good? So let's see where have these algorithms been used before. First, what they are, you basically use a faster computer and you get some acceleration, right? You change the processor speed or the number of cores. You use parallelization or vectorization. Or you can use programming techniques. You block your for loops and things like that. You avoid using inheritance, for instance. And you get various factors for each of those, between 2 and 7, 2 and 10, but the most acceleration that you get from numerical methods. And that is because a lot of algorithms are iterative, and you do a lot of work that probably you should not do. So design principles, that's for the type of code that we've been writing. It's not use inheritance, virtualization, and things like that. Portability, so that you do not depend on somebody else's software. And F77 free, user-friendly. That means that I might write in my code something advanced in C++, but for the other people that use my code, it would be like Fortran. That's important to keep this Fortran style in mind, because as scientists, Fortran is the natural way that algorithmic way that we are thinking. So that's very important, and that encourages people to develop their own code. Quasi-polymorphism is the ability to change the same algorithms from one type of data to another type of data so that you do not rewrite the whole thing again. And just to underline, the biggest acceleration that you get is by using math, so algorithms. Where this has been used before, you can see here, for instance, this collaboration is basically using it for pattern reconstruction and track fitting. And this is particularly useful for online monitoring and trigger applications. They've been using, well, some people have been using various algorithms that avoid iterative procedures and transform a nonlinear problem into a linear one. For instance, this projection on the Riemann sphere transforms a line into a circle and the circle into a circle. And since we have curved tracks, the idea is that you have this plane here in which the circle stays, and you fit for that plane. And that's a linear problem. You can see what happens here when you move this circle and you have errors on the points that you get to be in another plane on the sphere, and so on. It moves the errors non-linearly, and although you get the acceleration that you want from avoiding iterative procedures, you're changing the problem from 2 dimensions to 3 dimensions. And since this scales like the Gauss-Jordan problem, you're basically losing about half an order of magnitude in speed just from going from 2 dimensions into 3 dimensions, because in 3 dimensions you just have more computation complexity. Another area is vertexing. This, again, is a nonlinear problem. There's the famous paper of Billoir. But Billoir, in all his papers, he has this matrix type of approach, and this matrix of matrices and vectors of vectors, and that is slow. I've done some work myself. I basically write a helix like this for some reasons that will be apparent here. The first part is a straight track, and in high energy physics, a lot of tracks are just straight. Or you can have some second order correction or third order correction. Okay, so it's good to keep that in mind because that saves computation time. And when you do vertexing, you have a linear solution for this type of tracks. And you can perturbatively move the vertex to a new position by adding a correction that corresponds to these terms here. And then you get an algorithmic solution, a fast solution. And this I published here. And for track fits, that's another paper I published. So what's the motivation for this? This comes from history, from Atlas. You have all these hits in the detector, and the number of combinations is huge in forming these tracks here, right? So you have to check if this hit here goes with that hit there, and so on and so forth. The number of combinations is perhaps greater than the atoms in the universe or something. So you need a routine that is very fast in forming tracks for pattern recognition. And as you use these combinations, you have to reject most of them very fast within the first few computations, right? And then the rest of them you can afford more time. And that's the load that you get here in pale blue. You see that this one at the beginning is the one that is most used. So that's why it has to be very fast. And in doing that, we prefer to select hits that we want to look at. So very basic requirements such as, for instance, hits that are outside this region would not come from the interaction point or an area that might be a B or a D meson that flies away from the IP. It might not look like half an ellipse, but to me, this area looks like half an ellipse because half an ellipse is very fast to calculate. And you have this formula for half an ellipse, and it takes only 10 operations to calculate this, where R and R prime refer to this hit and some other hit in the middle, because you start from the outside in. And actually, the same thing. You have to see the range of the interaction point in a sort of a view, and the hits that you're looking at are inside this range, and inside that range you have another formula like that that looks even simpler, but it has just 4 more operations because square root is equal to 4 operations. So in doing pattern recognition, you have all these steps of being on the same side of the interaction point, of satisfying axial and azimuthal confinement, and then you write all the hits that are in that area of interest to a list. And looping over a list is very fast, right? So this region of interest definition, what you see there is about 28 operations, and in vectorized optimization form, that's about 3 nanoseconds. That's really fast. Then when you loop over the list itself, you just have 4 dereferences in this small list. And you have a routine that keeps adding points to the set of points of the track that you are trying to fit. Okay, and of course, remember, if you want fast, forget all these fancy type of constructs and stick to C++. Now, what plan do I see for SPD? Okay, first, what is the problem? The problem is not fitting tracks exactly, but having an approximate fit to be used for event selection. Igor, am I right? Okay, so that we do not have biases. Okay, so basically we have an abbreviated version of track reconstruction that has the requirement to be very, very fast. Okay, so the idea then that I propose is that we do a 2-step pattern recognition. First, we form segments, a few hits, say within groups of 6 straws, and we form a segment. A segment has the advantage that it's linear, and a linear fit is fast. And then we group segments to form a track. So it's possible to do this because our resolution, which is about 130 microns, if you look for 6 straws, that means 3 here and 3 here, and you take a line versus a curved track, it's indiscernible within our resolution. Actually, the fitted line goes through the middle of this segment, and it's 75 with 75. You can actually afford 8 straws, 4 plus 4, because it goes quadratically. And then, as I said, assemble the segments. So heuristically, this is back of the envelope calculation, it's not exact. But in forming groups of 6 hits, we have a C6n number of combinations. And then the number of segments that are left, combine all with all, we have n over 6 factorial. In reality, it's much less than this because each segment points to the next segment, so you don't take all combinations with all combinations. You just go, you look in a cone, the segment points to a cone, and within that cone you find the next segment, and so on. It's much faster than this. But anyway, if you would just loop over all hits and take all combinations, you would have n factorial. Okay, so what does this mean? Let's say we have 3 tracks with 10 hits each in a region of interest. So then we have 30 hits. The above equations translates into 10 to the 7, much less than 10 to the 32. You can see the difference. I mean, even if this calculation is not exact, you can see the problem and why I propose this split type of pattern recognition. So is it party time? Well, not yet, but it's encouraging. So this is the plan for work. Initially, I started thinking about this routine here, a fast track fit, and I realized that you need all these other things here. So here you assemble segments into a helix, into a track. But you have to do first the fit that gives you the segments. If you want a fit that gives you the segments, you have to have a hit provider. And since this thing here waits for somebody to give it a set of points, of hits, you have to have a pattern recognition. And the same on the other side. So that's how a simple problem becomes a complex problem. Okay, so the segment, the hit provider, Basically, you want to generate a track and then intersect it with the straws. So that's the general idea. Again, this is not possible. So you know how to intersect straight lines, but helix with straight line, which is a straw, it's not so easy. But you can treat it perturbatively, and you change the simple one to the more complex one. Here you have, this is the simple linear, and then you have this gamma, which is the nonlinear, and this is the straw here, this linear one. And okay, fine, you treat this perturbatively and you get an analytical solution for the deviation of the position of the distance of closest approach, okay? In the end, you manage to do it, so you can do this type of thing and find these little distances of closest approach. And you give it the track parameters that goes into the straw detector, and it will give you the distances of closest approach. You know, can list them like that. And now about pattern recognition. I've been doing a little bit of thinking about this. I did not have much time because I worked on the helix fit. So this is how the straws are in SPD. Some are aligned with a beam line, and the others are, you know, at a small angle. I think it's about 6 degrees or something. Okay, so let's say these two have a hit. In this plane, they are one on top of the other, and in that plane, this one is on top of the neighbor. So for pattern recognition, this is confusing, right? So need to determine the plane of vision so that you can determine the guess solution. Okay, a bit about the straw problem. The straws are not pixel detectors, as I started thinking about doing fast fits. And they have this information that they give with distance of closest approach. You get a signal for all these avalanches here, but the most reliable information is the closest one, this one. And you get the distance of closest approach to the center of the straw. So you record the drift time, you record the signal, and this is your time of closest approach, the avalanche that reached the first, the wire, the anode. And you want some translation between time and distance, and you have some calibration curve that looks like that. Okay, how are they arranged? The straws, they are layers. This one is parallel with the beam line. This one is tilted that way, and this one is tilted the other way. And then you assemble many of these into something like this. And then you have around the clock 8 of these octants. So it's called a ZUV arrangement. So the mathematical problem in determining a track fit is actually finding a track that is tangent to all these cylinders of given radius, of the colored radius. That's sort of nice when you see it in 2D, but in 3D, it's like this. So help, need a salvage operation. Anything is possible until you have to do it yourself. So yeah, how do we go about doing this? Well, first, the track, we call it a linear track. As I said, we find segments. For a segment, we have a straight track. The straw is also a straight line, and distance of minimal approach between two lines is this. Okay, I'll skip some of the details, have to keep track of the sign. Now, you start with a guess solution, and you do a correction. You find these terms that are the change in offset and the change in direction of the line that you are fitting. And this is all linear. You get this system of 6 by 6. And that, well, okay, fine, keeping track of details. There's a routine that I have for fast Gauss-Jordan that I intend to make it even faster by acknowledging, you see this is a symmetric matrix, so it will become about twice faster. That's timing for complex numbers. You see it's highly parallel because you see that the user has about 9 times the real time. So this is, all these equations that I wrote before are here. And that's 99 operations, which in optimized form, it's about 8 nanoseconds per straw involved in the fit. If there's 6, that's just 50 nanoseconds. Okay, so coming back to the hit provider and that initial guess solution that I was talking about, this is how you see the hits from one track in various planes perpendicular to the straws. This is correct. And these are in different other planes. So I'm working on this and finding the focal plane, to call it, so that can take the initial guess solution. Okay, what if that does not work, that linear fitter does not work? Well, you can always do a neural inverter with 2-3 mid layers of neurons, and you're worried about llama hallucinations. There's a paper on this thing that llamas and ourselves do not see things the same way. And this paper shows you how a llama sees a bear. We both say it's a bear, but the llama sees a total mosaic, mumble-jumble of a picture. So we are worried that basically people worry about this llama hallucination problem that when you train a neural network, it depends a lot on the noise in your simulated Monte Carlo. Because you worry that the real data might have a different type of noise, and then the neural network becomes biased. I tell you that it's not such a big problem for this type of linear regression problem, where you take basically the whole space, you generate tracks and all angles, and you make the neural network recognize the track as it produces these distances of closest approach. So this is a fallback solution. It's more intensive work because you have to generate the whole space of combinations, all angles, all offsets with respect to the straws and so on. It's doable in case the linear one does not work, but I hope the linear one works. So in the end, one method or the other method, what do we get? We get the segments. Practically, that means we get the center of the segment, and that's an XYZ information. Additionally, we get the direction of the segment, so the tangents. And then for pattern recognition, this is good because this points to the next, that points to the next, and so on. So that's fast. Okay. Now, XYZ, we're back in business because now we can actually do stuff the way we knew to do it from pixel detectors. So we take a helix and we expand it, please, here. We expand it around the point of closest approach to the beamline, and then we have that type of expansion that we can work with. I come back to this equation of the helix and project it in the transverse plane to the beamline. And project it also longitudinally. So you have two fits that you do. Split the helix fit. This is not an exact helix fit. This is a fast helix fit. Split it into two, a circle fit and a linear regression. For the circle, observe that the norm of this part here is r, the radius of curvature. That means if you subtract r0 from r perpendicular and take the norm, you basically get the sign of this running parameter. And then you take the arc sign, and you have your running parameter here. And you can check the linearity of this formula. If the linearity is good, you have a helix. If it's not, it means your points, your hits actually have a different clock frame than your hits on the circle. So basically this check means that these two pictures have the same clock, use the same clock. Basically this running parameter. So, as I say, you take this thing, you find your x, you put it into the arc sign, and you go there and you check. Okay, this is very fast. That's the whole point of the exercise, and you check if this is good, if this chi-squared divided by the variance of z. Okay, and that conditions the helix line correlation. For the circle fit, there are two methods. I will not go over them. This one has a nice chi-squared in closed form, so then the advantage is that you do not do the fit, you just do the chi-squared calculation and check for points that satisfy. This is an alternative fit where you just take sets of 2 points and draw the mediator, and then you do flash vertexing, because once you have all these lines, you can vertex to get the center of the circle like that. So this is an alternative solution that I have not found it on the internet. The previous one, you can find it. Another aspect here is that, of course, for sets of just a few straws, you can neglect the torsion. And when you do, since we have segments, we have the tangents. The tangents are the derivative of this formula, and they are linear. You see, so that's attractive because linear methods are fast in obtaining the parameters. I have not implemented this because the error on segments that are based on just 6 hits is rather large, and you do not get a good estimate. But the tangent is good in pattern recognition in pointing to the next and to the next segment. Okay, the timing of the circle plus linear regression is this. You can see that for 30 hit fit, you get something on the order of, I don't know, 100 or something, I don't know. I don't know exactly. Anyway, something there. And you multiply with the 30 hits, and you get something like 1,800 nanoseconds per helix fit. 30 hits. So that's very fast. That's extremely fast. The only review on fast helix fits I found is this. There's work of Fruviat and Strandli. They've been doing for 20 years this kind of thing. And they say that most methods are within range of the Kalman filter fit. So, you know, there's very small differences, 30% or something like that, depending on multiple scattering simulation level and the type of fit that you do. They argue, okay, the Riemann sphere that I've shown you is the fastest, and indeed it has fast performance for low-level multiple scattering. But still, this is not the type of acceleration that you want. You know, 30% is equal to nothing. And, you know, there are faster methods that people have implemented. So this is more recent, from 2 years ago. And what you get is something like this, 4 milliseconds per track. Okay? We are much faster. So I mean, 30%, things like that are nothing. This is not optimized. This figure is not fair. First, they do a complete fit, and we do just an approximate fit. And second, they use GPU and we use CPU. So if you would run this on a GPU in highly parallel mode, you would get about another factor of 5. So that would bring it to 10,000 faster. And if I optimize the code more, I will get another factor of 2, so we'll go to something like 20,000 times faster. So now that's fast. So, okay, where are we? This is done. These two, I'm working on them. And do not forget that this is a big job for Atlas. It took 15 years. Of course, they had multiple packages because Atlas is a big collaboration. But yeah, Flash algorithms, as I've shown you, analytical methods are the key to big speed-up factors, really big. Linear methods are viable. They look interesting, go promising. And CPU-wise, so far, we are the best there is. Спасибо.
Thank you, Mihai. It's a very nice report. And did you check your algorithm for simulation, for SPD simulation? Not yet.
For now, that's why I'm building this infrastructure to generate hits and generate segments, because I have to control everything. I cannot use giant data because that comes in fixed format. I want to change this, that all the time so that I check that it does the right thing. It's preliminary data that you have seen. I was in Samara, I came here, so there was not enough time to do a lot of checking and a lot of optimization. At the end, it will be JN4. For now, it's these generators of my own, both for hits and for segments.
Okay. In the future, it will be interesting to see the efficiency depending from the polar angle, from the point of the track origin, also, and for momentum of the track.
A lot of tests are interesting. Speed and resolution and dependence on the track parameters. Look, the helix fit has no preferences. It will give you an answer always. It will be the correct answer if you have 0 errors on the hits. If you have errors on the hits, it will be approximate, but it will be the best approximation that you can get. It does not take DDX into consideration, but that's what you do for a fast fit. The pattern recognition, that will depend on track parameters. The helix fit not.
Okay, thank you. Please, questions?
I have one comment and one question. Could you show your first slide with straw tubes? So unfortunately, you do not have slide numbers. It's better to start from the beginning of your presentation.
It goes faster backwards.
Okay, it will take some time.
No, not
but
here.
okay,
Here
I can
not.
start.
Okay, wait.
Such approximate but fast algorithms are especially interesting for us at the level of online filter. So when we just collected the event and
Where do you want
we should decide what to do. So identify it, maybe roughly reconstruct the moment and so on. But no, before. When you have numbers for resolutions.
Here?
No, before. Yeah, this one. So, but at this level, at the very beginning, we would not expect such fine resolution for our straw tubes. So 150 microns, that's for well-calibrated
Yes.
detector. So at In the online filter, we would expect a resolution a few times worse, even maybe one order of magnitude worse. So how this fact changes the situation for you?
It doesn't.
So maybe you can simplify your algorithms even more.
Yeah, exactly. That's the only way. So you're right that I could have said, okay, let's use groups of 16 straws. And then it would have been more and the error would have been bigger, and because of what you say, it would have been acceptable. But I said, let's stick with this. You know? I mean, this is, doing it better. I would need actually 8 straws, but 8 straws is still within 150 microns. So 8 straws because you need, let me, you see, no, sorry, just a moment. This problem, so if you change the plane, the Z straws always match. So I need Z, U, V, Z, and match, sandwich them between 2 Z's, and then look for the image plane between 2 Z's. So that's why I need 8 straws. But 8 is, I don't need more than 8.
Okay, my second question, so you absolutely correctly said that we need to have fast and unbiased method to reconstruct tracks. But how you can guarantee that your method is unbiased? How it is robust against uncorrelated noise and correlated noise? So maybe it's too early to ask this question, but in any case, unbiased is more important for us than the speed of this algorithm.
I do not know how the biased or the unbiased noise looks like.
No, but it will be simply additional step in your exercises, just to add uncorrelated and correlated noise and try to compare reconstructed parameters and generated.
Yeah, well, with these generators that I'm building, I can do all these tests before running on GENT data. I will have to talk with Igor or with you how to generate the type of noise that we are interested in. Yeah, we can do this type of thing.
Okay.
I'm sorry. Mihai, as computing guy, for me interesting, how did you compare your method with other methods you mentioned? For example, you mentioned GPU is much slower.
I looked, they run on samples that they take from GENT, and they do not do pattern recognition. So in this respect, the comparison is fair. I do not do pattern recognition, they do not do pattern recognition. So we're basically comparing just the fit times. They say for a number of tracks, and I divided the time that it took them by the number of tracks, and I got the 4 milliseconds that they have. For low number of tracks, because the GPUs are more parallel, the GPUs compensate the type of Gauss-Jordan type complexity. With parallelism, they have 2 milliseconds per track. For higher number of tracks, they have 4 milliseconds. But in any case, it's milliseconds per track compared to the speed that I obtained for, for 30
I would say that the correct test is just try your methods, and for the same geometry, try their methods. And this is something. So this is not a direct comparison you mentioned. Okay, no problem.
Well, okay, fine. The GANT4 simulation gives you a number of tracks, some with 10 hits, some with 30 hits, so okay, and they did it for the LHCb context, I think.
And
Who knows?
just another question. Did you show your message algorithm for other experts, for example, for loops or for Atlas people? Not?
When?
I don't know.
When? It's just no time. I just barely came from somewhere. I was working on this thing. And I'm not sure, okay, you guys decide who you want to show this. I will make it available in GRNR lib. And if you decide you want to show it to other people, okay, if not, not. I do not particularly intend to share it with anybody.
Thank you.
I have a question about GPUs and specific implementation, whether you think of that. So likely our primary processing, like data unit is time slice of something like 1 to 10 microseconds. So we'll have like not one event, but actually some number of events there, and GPUs should allow to parallelize a lot of things. So you wrote some code. So if you go to GPU and intend to do some highly parallel implementation of that, will it how much work that would require? Would it require significant redesign of the test samples? Not test, but
you ask a difficult question. GPUs require parallelization, so have to get to know what, for processor I know it's OMP and I know how to use OMP. For GPU I haven't used it. I have to see what type of commands are for parallelization. Also for processors I know this code has been with SIMD, which is using the multiple arithmetic logic units from the processors. I do not know if GPUs have that facility or not. Have to check on that also. Also note that the GPU is 5 times slower and 5 times faster. If you use it in single thread mode, it's about 5 times slower. If you use it in highly parallel mode, it's about 5 times faster. So you have to see if your problem really uses the parallelisms. If not, it's not faster. The CPU is faster.
Thanks a lot. This looks very inspiring, but I have the similar question on the GPUs. So the fact that you are too much faster than GPU on CPU than on GPU is basically because you are using much smaller arrays and much smaller parallelism. If you want to go to GPU, you will have to utilize the old GPU in parallel to be efficient. And most probably these Kalman guys is what they're doing. They use full information and they fill most of the memory and use most of the threads on GPU. So what is your assumption or what is your plan to scale your problem to the GPU scale?
First, make it work well on CPU, and after that, worry about the GPU.
Well, you say that on GPU you expect it to be 10,000 times faster, and so is there a basis for this?
It would be possible if somebody would do that, but for the time being, I mean, look, I have to solve the physics problem first, and after that, worry about the computing. For now, I know how to do on CPU, and I don't need to learn anything, so I can basically just go and do it. For GPU, I have to learn how to do it, and after that, do it.
So this may happen that this is not 10,000 times, and just much smaller.
I don't know. So, look, if you run into this rut that you are not really using the parallelism of the GPU, then it's not going to be faster.
Yep.
Yeah, that's the point. So you have to really make sure that you have a problem, or basically what they are doing, you know, they have reconstructed up to 100,000 tracks, 100,000 tracks, right? So what happened? They just gave each GPU a track, or 100 tracks. That's a simple type of parallelism. It's not the same as splitting your task to be parallel. They are two different things. And basically, their solution is no different than using 5 computers or 100 computers. You can also do it like that with MPICH.
Do you want to say they use one track at one GPU, or they split GPU and subparts?
My assumption, but I have not understood from the paper because it doesn't really say, is that they give each GPU a track. It's not that they give each GPU a part of the job of fitting a track.
Okay, thank you.
Yeah.
More questions from Zoom? Okay, thanks a lot.
Thank you.
Thank you.
Спасибо.